In this brief video, I want to expand a little bit on the concept of quality assurance, which we discussed a little in the earlier video. I want to talk about the blanks and duplicates. Now, in this particular case, you'll notice for blanks, they're not to be deployed, but the lab has to think that they were deployed. So, when you get, let's say you're going to use charcoal canisters, you're going to get them probably in a bag like this, and we already talked about this. In order to deploy the detector, normally you would take it out of the bag, and so you would have the detector and you would put it out. Now the detector is sealed by this sealing cover, and the key here is a blank is you don't want to unseal it. You're simply going to leave it sealed, and in the device placement log form, you're going to indicate a blank. The charcoal canisters, they're easy to deal with because once you indicate on the device placement log form that it's been deployed, the lab's going to think it's been deployed. They're going to get it back like this, and they can't tell that it has not been deployed. And that's the goal, of course. We don't want them to know that ahead of time. When we talk about the charcoal trays, which we've discussed earlier, they come in a bag like this, and the bag has, of course, the charcoal tray, and it has a set of instructions and a form to fill out, and it also has that aluminized envelope in it. So what you need to do is you have to make the laboratory think it was deployed without ever having deployed it. So what you're going to do in this case is you will remove the inner bag from the outer bag, and that has the charcoal tray in it, and it's still sealed. Now you don't want to send it back like this because then the lab will know it's never been opened. What you've got to do in this case now is you have to take it out of its bag, the inner bag. And then as soon as you take it out of the inner bag, then you want to put it in the return envelope, which is the aluminized bag, slipping it in here, putting the serial number on the outside of the envelope as is indicated, and sealing it, and then sending it back. Now, the truth of the matter is, when you took it out of that inner bag and took a few seconds and stuck it into this bag, it was deployed, but really only for 10 or 15 seconds, and we're simply going to ignore that. It should not have collected any amount of radon to speak of in that amount of time. So now, when the lab gets it, it will think it was deployed because it was indicated as such on the device placement log form, but in fact, it was never deployed, and that's precisely the goal for blanks. And here you see on the device placement log form, I've indicated that B for a blank, and notice no location, the serial number of the detector, and then I've entered some start date and start time, as if it had been deployed, but it wasn't. So this data is untrue, and that's okay. And then, of course, when I get the stop date and stop time, we will put those numbers in here as well. We want to make the line of information look as if it had been deployed. And remember, when you make a copy of the device placement log form to be returned to the lab, you will not make a copy of the two columns that are here in yellow. Okay? So, depending on the detector that you use, whether it's the charcoal tray, the charcoal can, or other kinds of devices, of which there are numerous ones, you have to be astute a little bit to make sure that when the blanks are returned to the lab, they appear to have been deployed when in fact they had not been deployed. Next, I want to consider duplicates and how we treat the quality assurance for those. And I remind you that a duplicate pair is just where you've deployed two detectors in the same location, 4 inches apart, of course, but fundamentally in the same place. And so those two detectors will bring back values for you, two values, one for one detector and one for the other detector. And the goal is those two values should be close to one another. Now, how close should they be? Should they be between a value of 5? Let's say one is a value of 5 and the other is a value of 6. Would that be close enough? Probably. How about 5 and 7? I'd probably be okay with that. How about 5 and 10? That would start to trouble me. And how do we identify when the difference is too big and we should do something about it? The EPA doesn't leave us out in the lurch on this. They're going to tell us how to do that. And that's what this quality assurance duplicate log is going to do. So let me just show you what you have here. You have, 5 columns. And the first column is headlined with D1. That's to represent the value of the first duplicate. D2, the value of the second in a duplicate pair. This is going to be the mean or the average value. And then these others I'll explain as we get going. So here's what a duplicate log could look like. And you see here that the first row represents the first duplicate pair, 1.4 and 1.2, two different values. And it doesn't matter which one you call D1 and which one you call D2, as you will see. And what goes in here is the average value. Now, how do you get the average value? That is simply the sum of the two divided by 2. So if I add these two, I get 2.6. And if I divide by 2, I'll end up with 1.3. And I think I can make the formulas a little bit bigger for you so you can see them right off the bat. Here's the average value, D1 plus D2 over 2. And then we're going to calculate this parameter called the relative percent difference. And it's calculated by taking the difference in the two values, divided by the average, and then multiplied by 100. Okay? So let's do that. Now, we won't be calculating the RPD right away. We're going to calculate that in just a minute. But recognize that we are going to calculate all the average values. So let's take another one. This is 0.8 and 1.1. To calculate the average, that's the sum of the two, which is 1.9 divided by 2 with a little bit of rounding gives you 1, and et cetera, we calculate all the average values. Now, we put an X in this column in whatever rows have an average value greater than or equal to 4. So notice that this first row's average value is not greater than or equal to 0. There is no X there, etc. Here, this average value is 4.9, and so we've put an X here, we've put an X here, 1 here, and 1 here, and nowhere else. So the total number of X's you see is 4. Now we calculate the RPDs, and the formula here says you take the difference in the values and divide it by the average. Well, we have all that data here, so let's take a look at this one. We have a D1 of 4.8 and a D2 of 5.1. Excuse me, that's a 4.6 and 5.1. So first we calculate the difference. That's the RPD is going to be the difference over the average and then multiplied by 100. So the difference is 0.5. 4.6 to 5.1 is 0.5. Now, if you do the subtraction in one way, you'll get a positive 0.5, and the other way, you'll get a value of minus 0.5. Always take it as a positive value. So in this case, it would be the difference is 0.5. And then you divide that by the average of 4.9. So take your calculator and take 0.5 divided by 4.9. You'll see that comes out to be 0.102. Then multiply by 100, as is indicated by the formula, and you'll get 10.2. Let's do one more. Let's take this next row, has an X in it, and it has values of 4.1 and 3.8. So the difference between the two, I'm going to calculate the RPD now. That requires the difference between the two as 0.3. And I'm going to divide it by the average of 4. Now 0.3 divided by 4, I'm really just doing this little calculation up here. 0.3 divided by 4 is 0.75. Multiplied by 100 gives me 7.5. Excuse me, 0.3 divided by 4 is 0.075. 0.075. Then we multiply that by 100 and we get 7.5. And we do the same kind of calculation for the RPD for these two, which also have X's, and we get 11.8 and 19.5. Now we take all four of these values and we add them up to get what we're calling the total RPD, the total relative percent difference. And we're going to calculate what's called the average RPD, and you can see it's given here. The average RPD is the total RPD over the number of samples. So in our case, the total RPD is 49, and the total number of samples is 4. So 49 over 4 comes out to be 12.3. And now you just check to make sure that that average relative percent difference comes out to be less than 25%. And if it is less than 25%, then you're done with the RPD calculation. So you should have, as results for your quality assurance plan, blanks all coming in less than 0.5 or thereabouts, and the average RPD coming in at less than 25%. Now, if you get a case where that is not so, that is the blanks reading 10 and the total RPD is 75, either or of those values, then I would suggest the next thing to do is take a look at your own data and make sure all your data is right. You've got all the numbers in the right blocks. You've copied the resulting values back into your device placement log in the appropriate place and put them onto these duplicate log sheets correctly. Assuming all of that comes out okay, then I'd contact the lab and I'd ask the lab, hey, I've got blanks that are showing 10s. What should I do about this? And see what response you get from them. You may find a very satisfactory response. But if you find an unsatisfactory response, then I would suggest you contact the Pennsylvania DEP and get some guidance from them. So the two conditions that you're looking at is all the blanks have to come in under 0.5 or so, and the total RPD, or the average RPD rather, has to come in under 25%. Either of those cases requires that you look into it a little bit further. I present to you now a device placement log that we fabricated with some errors in it to make this a little more entertaining and interactive for you. There are numerous errors in this device placement log, one of which people generally do not get. So I'd like you to take a minute or two and look over it and see what errors you can come up with. And then come back to this point and we'll continue on with the video program. And I'll come back to this device placement log in a little while and go over the errors that are in fact in it. One more slide I wanted to put on here is this one here, which is a schoolroom that was measured by the Pennsylvania DEP. And what's plotted on this graph is time from left to right, and these are different days. And you can see this is a Saturday, Sunday, Monday, etc. And two plots are plotted here. There's the radon concentration, which is this darker graph, slightly darker, and the working level, which is a number that we are not going to be concerned with, but you'll notice that does have the same kinds of fluctuations as the radon concentration. And the point of this is to show you that the radon concentration fluctuates pretty significantly from day to day. And you'll notice these fluctuations are mostly daily fluctuations. Now you have numerous fluctuations during the day, these little bumps, but you also have significant fluctuations day to day. which is why the DEP recommends that you should not do a measurement for one day. In fact, you're not permitted to do a measurement for one day unless you're doing diagnostics. But for testing purposes, all your measurements must be at least 2 days so you can get a better average value. And clearly, the best average value you would get would be a weekly average value, a Monday through Friday, a 5-day average value. That would be about the best you can get using short-term detectors. Be careful, though. Not all short-term detectors can be used for 5 days. And in fact, the tray detectors, those with the trays that we've looked at, they have a maximum deployment period of 4 days. So that the most you could do is Monday through Thursday, not more than 96 hours. In fact, they tell you if you deploy it more than 96 hours, they will not be able to analyze it. So you've got to deploy it, that particular detector, between 48 hours and 96 hours. Some of the charcoal cans can go the 5 days, so there might be a little advantage to you there for going 5 days with a charcoal can. But I just wanted you to see that you get pretty significant fluctuations. And if you did just a 1-day measurement, for example, suppose your measurement was across here, you might think, wow, I don't have any radon in that room at all to speak of. That room is golden, when in fact the radon concentration may vary significantly. And bear in mind that when you're using short-term kits, you're going to do an initial value and you're going to do a follow-up in those rooms that are suspect. That is, those rooms whose initial value came up greater than or equal to 4. You're going to do a follow-up measurement on those. So for those rooms, you're going to have at least 4 days of measurements about which you'll average. And then as the last slide in this video, I want to take a look at this. Here's a storage room whose radon concentration was measured, and the radon is plotted on this axis, and the wind velocity is plotted on this axis in miles an hour, and the radon is in red, and you'll notice the radon does relatively small fluctuations compared to this big rise in the radon concentration. You might ask, gee, what would cause a rise in the radon concentration like that? And take a look at the wind velocity. You think the wind velocity is here, it looks around 7-8 miles an hour, hanging in around 7-8 miles an hour. And at this particular time, it starts scooting up and it provides values up around 35-40 miles an hour, and then it's coming back down again. And notice what happens to the radon concentration. Shortly after the wind starts rising, the radon concentration goes up to almost 400. And that's from a value of somewhere around maybe 20. So it's gone up by a factor of 20 just due to the winds. And I wanted to show you that just so you could see the effect that winds have. And so you need to be careful to try to not do your deployments when you intentionally know that the winds are going to be getting high. Now let me begin by reviewing the device placement log that had a bunch of errors in it. And we can start with the location, for example, and inspect each location, see if it was a good location. This south wall cabinet's probably fine. Teacher's desk is fine. Left windowsill, that's poor. We know we want to keep them away from windows. Center bookshelf might be okay. Here's one on the floor. Well, that's a terrible location. We're trying to measure the average radon concentration in the breathable air, and there are not too many people breathing the air on the floor. Above the first ceiling tile is a terrible location, as that is never going to sample the air in the room. In the left top drawer of the teacher's desk, that's a terrible location as well, because as the room concentration of radon changes, this detector will not be able to keep up with that in any way. And on the file cabinet in the rear, that's probably okay. If you review the serial numbers, they all look okay. There's no special ranking to the serial numbers. As we look at the start dates, we find right away one of the start dates appears to be a problem. Here's one that was started 3 days before the preceding one, and 3 days preceding the next one. And yet the times all follow in a reasonable sequence. So it's likely that this is a typo, but nevertheless, it's an error. And also for this particular detector, notice it was retrieved 6 days before it was deployed. Clearly not possible. So that's unfortunate. Now, the other error that many people don't get is that there are 2 rooms labeled as 102, meaning it would be very difficult when you get the results back to identify which detector was in which room. So that's just to underline that you have to be careful with how you identify the rooms. Thank you.